Hello. We are looking at the Flax library for doing neural networks with Jax. We looked at Flax previously as part of the stream on reinforcement learning. We didn't dig too deep into it. In that stream, I was mostly looking to get a feel for what the code was like, what sorts of like a basic gist of what the concepts were. And since then, over the weekend, I had a little time and I tried implementing a couple of things in Flax, and some of it worked, some of it did not. And I couldn't quite figure everything out from the documentation, how things were supposed to wire together. And the AIs were totally useless. The AIs kept giving me plausible looking code in Python that was really using other libraries like Torch or some other older version of Flax. And so I thought the solution to that would be, let's actually take a look at the Flax code and see what we can see. So the main thing I wanted to look at is I want to look at the NNX Flax library. There's an older version of the Flax API, which is called Linen. Linen being a pun on Flax. And from what I understand, the Linen API is more functional. The NNX API is more object-oriented. So in a sense, it seems like maybe they went backwards from the functional craze to the OOP craze of the 90s. But they seem to have some reason for it. The other thing I've noticed is that not all of the bits and pieces that are available in Linen are also available in NNX. I don't know if that's a design decision. I don't know if they are slowly porting over functionality or what. But I want to get a sense of what's up in NNX. And as part of that, we may peer deeper under the hood, but I'm not making any promises. Okay, so here's some documentation. We're mostly going to ignore it. And for my purposes, I guess the main thing I want to see is I want to start getting a feeling for the different pieces of models, the different layers, I guess you might call them, when you're building a neural network, and how they connect to each other, how data flows between them, and also how the NNX and Flax authors use them themselves. So I guess as part of that, we may take a look at the not the testing. Where is it? Experimental? No. Examples. Somewhere there are examples. I guess it's up one directory. Also, GitHub twice has rate limited me today, despite only having done like 2 GitHub searches before. So I don't know if GitHub is experiencing problems, but we can always fall back on the local copy I cloned. Okay, so here's the NNX directory. Things like bridge, scripts, training, and transforms. I don't know if I'm ready to see them yet. I definitely want to take a look at NN. And a bunch of this stuff is probably important to understanding the Flax API in general. But right now, I just want to get a look at what's going on in the neural network place. And I was actually kind of thinking these would be folders. If you look at the API documentation, it has like attention, linear, etc. And I was anticipating that those were going to correspond to like folders full of information, but they appear to be single files, which seems to imply that there is probably a relatively small implementation. D types, I will guess, is probably related to the like NumPy D types. I don't know if this is like NNX support for the existing NumPy D types, or if they're like defining their own D types or something along those lines. I don't remember if I already opened attention, but let's also open activation. Okay, so attention is maybe, let's start at linear, because linear is almost certainly the simplest. So here's linear, and I also looked at. Let's see. I was unclear on some of the basic neural network stuff, how it related to the underlying math. The underlying math is mostly clear, but there are some kind of like weird things that the neural network people do, if I'm understanding what they're up to correctly. One is what they call linear is really affine. So it's a linear transformation composed with a translation along some vector, that vector being the bias. And so that's a little bit weird. They also, the thing that they call an embedding, unless I'm missing something, is generally not actually an embedding. It's not a one-to-one transformation. The way that we're supposed to think about it is that somehow the words are put into some semantic space that has a lot of that has some where words that are similar in some similarity space are similar in the vector space. However, you almost always, I think, we're embedding them into a vector space that space that's smaller than the number of than what the underlying similarity space is, and we're also moving from categorical data, which consists of different words, to the vector space. And if I'm understanding correctly, I don't think that there's any sort of proof that either of those maps is one-to-one. So those are just two things kind of to keep in mind. There's some there's a way that the terms are used in the neural network literature that may not be, if you're thinking about this literature from the perspective of the underlying math, then the word usage might not be correct. Hello, Ramadan. Schwab7? I assume you mean hello and not Halo, which is a game, I guess. Okay, so we have a bunch of stuff like padding. Padding, I think, will probably be important, but I think I'm not at the padding level yet. So here's linear general, a linear transformation with flexible axes. I don't know what it means for axes to be flexible. And this is claiming to be a linear transformation. So this should be a matrix. Let's go back up here. Linear general. And I don't know if it's, hang on. Stop this. Okay. So for example, you import some stuff. NNX linear 2.4 is equivalent to linear general 2.4 passing in some RNGs at RNGs of 0. I don't know if this 0 is initializing the random number generator with the 0 seed or what's going on. We may see that later. And then if we do this, then we get this thing back that's a layer. If we look at the layer and then look at its kernel, and then look at the value of the kernel, I guess, and look at its shape, which now I think is the shape in the sense of like a NumPy array shape, then that is 2, 4. And I think what that means is that it's like a 2x4 matrix, a map from a 2-dimensional vector space to a 4-dimensional vector space. And similarly, if we say linear general 2 to 4, 5, then we get back a kernel whose shape is 2, 4, 5, which now I think is a 3, like a whatever you call it, a 3 matrix thingy. And the bias value shape is 4, 5. So now the bias, I guess, is multi-dimensional, is like a matrix. And okay, so let's so Ramadan is saying it'll take them a long time to learn programming. Well, that might be okay. I think it takes a long time for lots of people to learn programming. Okay, so let's take a look at so one thing that I've noticed just in terms of like coding style, they call this example usage, but this is actually not really how you would use this. I think what's going on is this is really a doc test, and they're calling it example usage instead of something else. And this is really an embedded unit test, which is, I'm glad they have unit tests, but that this is maybe not the most interesting. It would be nice to have an actual usage example of what this might be up to. So we have in attributes, an int or tuple with a number of input features, out features, int or tuple with number of output features. We have an axis parameter, or attribute rather, which is with axes to apply the transformation on. For example, -2, -1 will apply the transformation to the last two axes. And I'm guessing that this is, you just have a list of the axes. I don't know if you have to list them in this backwards negative order. We'll see maybe how it's implemented. Or we may not, I don't know. A batch axis, mapping of batch axis indices to axis size. I'm not sure what's up with the batching. I'll talk about that in maybe a minute. Use bias, whether to add a bias to the output, default true. So that's the thing that makes it, I think, an affine map. D-type is the D-type of the computation, which it will, by default, will infer from the input in the parameters. I don't know when you would pass it in. Maybe you would pass it in if the inference fails, or if you're concerned maybe about the performance of inference. And then param D-type is the D-type passed to the parameter initializers, which by default is float 32. So float 32 is smaller than float 64. And I don't know what it means by the parameter initializers. I'm guessing this is maybe part of the internal state. And then a kernel initializer function for the weight matrix. The weight matrix, I think, is the actual linear transformation. A bias init, an initializer function for the bias. And I'm guessing that, I think mainly, and correct me if I'm wrong, mainly we, conceptually at least, we initialize neural networks randomly. But there is research that if you initialize them in specific ways, you get better performance or better convergence. I think mainly convergence. So I think that this is possibly just giving the user access to passing the initialization stuff into the constructor. And then some precision, which is the numerical precision of the computation. It says C Jax-Lax precision. I'm not entirely sure what the Jax-Lax library is. I think it has a lot of the fundamental stuff. We may have run into it last time. Lax of primitives operations that underpins libraries such as Jax.numpy. It has things like absolute hyperbolic cosine, arcsine, bitwise, or okay. Why is it called Lax? Well, they needed a Jax pun. I don't know what the L is for. Okay, and then we have some, for RNGs, we have an RNG key. It's describing it as a key as opposed to the generator itself. I think we've seen something similar to this. I don't remember if it was in Jax or somewhere else. The Jax.random package. Unlike the stateful pseudo-random number generators that users of NumPy and SciPy may be accustomed to, I kind of read this as like those rubes that use NumPy and SciPy with their stateful pseudo-random number generators. Jax random functions all require an explicit PRNG state to be passed as a first argument. The random state is described by a special array element type that we call a key, usually generated by the jax.random.key function. Okay, and so do we get an example of what when you call random.key of 0, you get some key back. And when you ask it for the key, it is, I don't know what this overlaying stuff is, but we get 0, 0. And so what is the point of that? The point of that, I think, is it just makes just like it's nice to have stateless services so that you can terminate services at will. It's nice to have stateless Jaxy numeric things that you're passing to the GPU, because then you can manage the state separately from the stuff, the thingy stuff. And that's all part of how they squeeze a lot of performance out of something like Jax. I was going to say something up here, which I think is about the batch access. Again, I think this is probably related to how Jax does like auto batching of things, auto like vectorizing and batching. And that is mainly, again, about optimizations for the GPU world that we live in. And then we have this initializer type. It looks like whatever precision like is. I'm not sure. Maybe like precision like is allowed to be a string or also a float. I don't know. We also have dot general T. And these will be removed, so I'm not going to look at them. But mostly we're just initializing stuff. Things have the appropriate type, and access is either an axis, whatever that is, or a tp.sequence of axis set to -1. Or rather, this is the type, and this is just the axis is by default -1. Which is the axis that they're going to apply the transformation to. So what is that about? I'm not sure. I think that's because like you often are dealing with like a large, like NumPy style or Panda style data frame. And instead of like sectioning out a particular column and passing it to the linear transformation, you can maybe pass the whole data frame, and it will the linear class will know how to access the appropriate column, and it might do that just by giving the whole thing to the GPU and like setting a lot of stuff to 0. I don't know. I don't know what the underlying optimizations are, but you can imagine a thing like that. And then we're keeping track of a bunch of stuff. We're calling this canonicalized tuple, presumably to just essentially sanitize user input. The batch access is a frozen dict, I guess from access to size of batch access, axis. And then we're just setting stuff. And when we call length, oh, no, sorry. This is just doing some computation. And if we have a batch axis, then the batch dimensions are, we're going to look at the tuple, or rather we're going to look at the batch access keys, cast it as a tuple. I don't know what the keys are, if these are the RNG keys or something else. Maybe, I guess, keys of the dictionary, since we just made it a dictionary, right? Up here. And those are the batch dims. And the maximum dim is the max of the batch dims. And we're going to cast the batch dims as a set, presumably to remove duplicates. And if it's not the same set as the range max dim plus 1, which are, I guess, all the numbers from 0 to the one more than the max dimension, then we say that the batch dims must be consecutive leading dimensions starting from 0. So I set up here, I didn't know if the axis stuff had to have this particular organization, but it seems to be like the case that that the batch stuff has to have that organization. They have to be consecutive. They have to start at 0. All right. Now, this was such a small thing, but I already have questions. One is, not being a regular NumPy user, I'm a little bit confused about this notation. I was thinking of the bias as something that lived in a vector space over a field, so like essentially a list of numbers, and that the bias, the thing that we add, I was thinking of as either a one-dimensional or a n-dimensional vector over a field. However, I think it's allowed to be a matrix. And so let's think a little bit about how to think about that. I guess first let's see if there's some documentation. Let's look up Jax Flax linear. I think ultimately this is probably like what they call tensors in the machine learning space. So if a 1D tensor is a vector, a 2D tensor is a matrix, a 3D tensor, they're thinking of as a cube. So a matrix is a 2x2, a matrix, a linear map over a vector space you can represent as a 2x2 array of numbers. And then a 3D tensor is a 3x3 array of numbers, and so on. And this is trying to, we can't visualize 4 dimensions, and so it's thinking of each, I guess, point as a cube here. I assume that this is really actually connected to the tensor product, but I'm not positive. So let's ask the AIs. So is a machine learning tensor, so tell me about what a machine learning tensor is. So is a related to the tensor product in math. Hello. So yes, a machine learning tensor is related to the mathematical concept of a tensor, including the tensor product, but they're used in slightly different contexts. Blah, blah. So what is the relationship? It refers to a multi-dimensional array of data. However, in machine learning, tensors are used more pragmatically as data structures. But I want to know, so a tensor creates a multilinear map. And I don't know if so for example, I don't know if a tensor in machine learning is used as a kind of multilinear map with all of the like structure that the tensor product gives you, or if it's just used as a convenient way to hold a bunch of floats. In mathematics, a tensor is a more abstract concept for multilinear algebra, used to describe geometric objects that generalize scalars, vectors, and matrices to more complex forms. They can be used to model things like forces, stress, and fields in physics. Okay, but are the in what field? What did I call the field? AI or machine learning? Machine learning. In machine learning, are tensors used as multilinear maps? More generally, do they have the structure of mathematical tensors? So they're not generally used as as multilinear maps. They store numerical data, and machine learning libraries are optimized to handle such operations efficiently. The tensors in these libraries are primarily viewed as containers for data, not as multilinear maps. For mathematics, tensors can represent multilinear maps. Okay. So some operations in machine learning implicitly use concepts from linear algebra, for example, tensor contractions during matrix multiplication, but the underlying framework typically abstracts that away. Yeah, but I want to understand the framework. Okay, so at least if you believe ChatGPT, which I'm not sure that I generally believe ChatGPT, then these aren't actually tensors in the usual sense. But I want to know this. Actually, maybe I could just look up linear neural network. I think that in general, this is just a fully connected network, right? What they're calling linear. So PyTorch is coming to the rescue, and it says it applies an affine linear transformation to the incoming data. Y equals X, A transpose. So we're multiplying X on the, A is acting on the right of X, and then we translate by B. And bias is a Boolean. There's something about ROCm devices. We'll use different precision for backward. And then here's some information about shape. So star HN, where star means any number of dimensions, including none. And HN is the number of features. That's the input. What is this star here? Input to what? Output is star H out, where all but the last dimensions are the same shape as the input, and H out is out features. I'm guessing that I'm not sure what we're inputting here. I guess this is like a constructor. And int features is an int. And I think that what it's saying is that like when you call the transformation, I guess you can have extra like columns that are not part of the input, perhaps. I also don't know what big H is, but maybe we'll just ask somebody about it. And then with the variables are what? I don't know what variables means in this context, but we have the weight, which is a tensor, the learning weights of the module of shape, out features, comma, in features. Okay, so this should basically be a matrix, since this should basically be A. And the bias is the learnable bias of the module of shape, out features. So it's a single int, as opposed to the documentation of the NNX thing, which seemed to imply that bias could be a bigger than an int. So I think that what they're describing as input and output here are the input and output of M, the function that's returned by the NN linear. All right, that's reasonable. And let's see what bias is. Wait, where did bias go? Use bias is just a Boolean. But I guess it seems like we can do, the output can be a tuple here. An int or tuple. So I don't know what it means for an output to be a tuple. Is there a linear general for PyTorch? Let's just ask the AIs. So in this method, what does it mean for output to have multiple dimensions? And it's saying instead of applying a linear transformation only to a fixed axis, like a traditional fully connected layer that transforms over the last axis of the input. So I guess this is tradition that we'll ask about this, but I assume what's going on again is you're passing in like a full data frame and you're just sectioning out a specific column So this class can apply linear transformations over multiple axes of the input tensor, allowing it to handle more complex data structures. The flexible axis argument allows you to specify over which axis the linear transformation should be applied, axes. This is powerful when dealing with multi-dimensional data like images, where you might want to apply a transformation to specific dimensions, like height and width. Yeah. But, okay. Bias, you can actually apply bias, weight, kernel, and bias, blah, blah, blah. That doesn't really answer my question, though. How can you apply a linear transformation that produces two vectors as output from a single vector of input? If you have an input, so it's saying think of it as into a higher dimensional vectors, higher dimensional space, but that's just a single vector in a higher dimensional space. Okay, well, maybe we'll just see what it does. And then let's just ask about this. When you say this thing about the, does that mean we can pass the function a full data frame and simply tell it which index holds the vector we want to transform? I don't know. I think it's possibly telling me something semi-related, but I don't think it's really getting to the point. Okay, so let's keep looking at this. I guess now my question is, can I figure out how they're going to produce, for example, let's say you have a single number of input and you want to get out 100 four-dimensional vectors. How are they going to do that? I don't know. Okay, so we have this kernel init wrap. This is presumably some function that's going to wrap the kernel. It's calling that's going to wrap the initialization of the kernel. And there's something about shaping. We're taking, I guess, probably products of a bunch of stuff, I guess, to get the size. Okay, actually, this is maybe interesting. So we're taking the product of what? So we're flattening, and we want to know what shape the flattened thing is. And so when do we actually flatten? So the flat shape we compute here, and then we reassign flat shape to be the jax.tree.map int of flat shape. Okay, so I guess this is a map maybe in the sense of a hash map as opposed to the Python map function, which I think is the thing in Python, or the traditional functional map function, which would map its first argument as a function over a list. I think this is just a hash map, I guess. And then we're calling self.kernel init, passing in the RNG and the flat shape, which now we believe is a hash map, and the D type. So that's going to somehow initialize a kernel, I guess probably randomly, with the correct D type and the correct shape. And then we look at something about whether the kernel is an instance of the variable metadata, which I'm not sure what that is. Otherwise, we're going to call reshape on the kernel with the given shape. So I think that kind of what we're doing is the shapes of the tensors are really kind of like a fiction for humans to worry about. And then under the hood, we're just dealing with like a flat shape. We're dealing with a I don't know how flat gets. But maybe a single vector or a single matrix. Perhaps. At any rate, we've got this batch shape thing. And then the kernel shape is going to be some combination of batch shape, the input features, and the output features. And I don't know what param is, but here we're calling kernel init wrap, which is maybe the thing that we passed in, right? No. It's the function we are in, right? This is a recursive call. No, this is the definition, I guess, of this is a function that we're defining inside of another function, I think, and here's just where it's called. And at some point, we're presumably going to call the kernel init function. Maybe we already called it up here. Here. Oh, no, that's linear, not linear general. You know what? I've been looking at linear general as if this was like a base case for linear, but I think it's a generalization of linear. And maybe I've just made everything harder for myself. But I guess that's not so big of a deal because at some point you're going to have to do it. But it does, I think, clarify a lot of things to me internally in my brain that if this is, we'll look at linear, and linear should be the case I think people typically use, and it won't be as unusual with respect to how it handles shapes and stuff, perhaps. But at any rate, there's some reshaping going on so that the shape of the thing that the GPU sees, I think, is not the shape of the thing that the humans are thinking about. And then we have this call function, which we're still in linear general, which is going to apply a linear transformation to the inputs along multiple dimensions. And the inputs are the ND array to be transformed, and the output is the transformed input. So we get the ndim from inputs.ndim, and the batch dims is the length of the batch axis. So we'll recall that batch axis was like a list of which, was it? I really, a mapping of batch axis indices to axis size. Axis size? So axis can be a tuple. And maybe it's saying that like the 0 corresponds to -2 and 1 corresponds to -1. Is that what the map is conveying? I don't know. But I'll assume that that's basically what it's conveying, in which case it's relatively simple. It just, I guess, gives you fast lookup or something. All right. The number of batch dimensions is the length of the batch axis thing, which is a dictionary. That's the that's the number of dimensions somehow. And then we're going to normalize the axes, calling it on self axis. I don't know what normalize is doing. Maybe this is, for example, putting them in numerical order. Then we'll call normalize axes on. We're going to get the keys from the back axis, which if the dictionary is the thing that I think it is, then those keys are what? The indices of the list we passed in. We're casting them as a tuple. And then the n axis is the length of the axis variable. And then we have this thing, batch and non-contracting dims of input with ones for batch dims. The expanded batch shape is some tuple where we're going to take the input's shape at AX if AX is in batch axis, else 1. So if X is in axis, or rather is in batch axis, then we're somehow, then I think that means we're intending to batch it, and we're going to add it to the batch shape if it's yeah. So the inputs has some shape, which might be like 2, 4. And if somehow 4 is in the batch access thing, then, or rather if 2, I think, is in the batch access thing, then this will be 4, I believe. Else 1, and then we're going to, oh, this is just a, what? I think this is just a list comprehension, but I'm not sure. I'm used to not seeing it with square brackets. Okay. So what else? So the kernel is just the self.kernel value. The bias is the self.bias value. The batch index is some tuple we get from here. We've got this promote D type thing, which I'm going to guess is just kind of like normalizing D types, promoting them somehow. I don't know how. Don't really care at this point. And if the self.general class is not none, then we'll set .general to the .general class. I don't know. I don't think I saw where they populated it, but maybe it's populated somehow. Else if the self.general is not none, then we set it to whatever that thing was. Basically, the thing that the version of .general that we've kept the record of with self, just like we did here. I guess class takes priority over non-class, assuming CLS is class. And then else, .general is lax.general. And I think that what the machine learning people call a dot product is they're including things like matrix multiplication as a dot product. Whereas that's generally just the application of a linear transformation, and a dot product is usually like an inner product that gives a different kind of structure. But I think that that's what they mean by a dot product. And then out is .general, and then it's going to consume some inputs, the kernel, and these things, axis contract ID, rather contract ind, batch axis, batch ind, and the precision is self.precision. So let's look at lax.general. And let's look up dot product. A dot product, or a scalar product, is an algebraic operation that takes 2 equal length sequences of numbers and returns a single number. Yeah. So right, among other things, the dot product is a linear transformation from it's a what's the word? It's a product of on a vector space, a linear map from two copies of the vector space into the scalar field. And I think that they're using it to mean things like matrix product as well. So Julio is saying, if I recall correctly, the numpy dot is both a dot when working with vectors and a matmul, matrix multiplication when working with matrices too. Yes, I think that's true. That's also kind of how R works. That things get like promoted to, essentially things are, they get promoted to maps is the programming way to think about them. And I assume that's what's going on under the hood as well. We're just basically like looping over a bunch of vectors and applying a dot product to them. And I guess that's probably why the matrix was acting on the right in that PyTorch example. Jax.lax.general, general dot product / contraction operator. It wraps XLA's .general operator. The semantics of .general are complicated, but most users should not have to use it directly. Okay, why are they complicated? I don't know if they're supposed to be complicated for math reasons or if it's complicated essentially for GPU reasons. But you give it a whoa. You have a left-hand side and a right-hand side of the operator. And you give it dimension numbers, a tuple of tuples, of sequences, of ints. So sequences of ints is a vector over the integers. Although, no. These are dimension numbers. I don't think we're supposed to think of these as vectors. But the tuples are of the form LHS contracting dims, RHS contracting dims, list LHS batch dims and RHS batch dims, just like we saw in the code that calls this in the precision. And it returns an array whose first dimensions are the shared batch dimensions, followed by the LHS non-contracting non-batch dimensions. Okay. And we have this note that in the XLA documentation, we have looked at OpenXLA, but OpenXLA is saying the exact semantics of this operation depend on the ranks of the operands. So for example, if the input, I'm guessing vector square n dot product vector square n, I'm guessing vector square n means something along the lines of this is a vector of length n, as in that's the type of the argument. It's like a, what's the word? A dependent type. So if you have two n by n vectors, I think this is what it's trying to say. The dot product is defined to be the vector dot product, which is a scalar. If it is if it's an m by k matrix on the left and a vector of k on the right, then it's matrix multiplication. You get an m vector. If you have an m by k matrix on the left and an k by n matrix on the right, then you can multiply these and you will get an m by n matrix. So it's matrix multiplication. Is that it? Is that really? So this is matrix multiplication. This is matrix multiplication after a transpose. But it seems like dot general was possibly doing more than just matrix multiplication. The operation also performs, the operation performs sum of products over the second dimension of left-hand side, or the first if it has rank 1, and the first dimension of right-hand side. These are the contracted dimensions. The contracted dimensions of LHS and RHS must be of the same size. So if you have this, for example, m by k and k by n, then the second dimension of LHS is the k, the first dimension of the RHS is the k. And these k's must match because you're taking the first row of the left-hand side and essentially and literally dotting it with the first column of the right-hand side, and those have to be the same dimension for that dot product to be on the rows and columns to be defined. And so those are the contracted dimensions, and they must be the same size. It can be useful to perform dot products between vectors, vector matrix multiplications, and matrix multiplications. Okay. Then what was underneath that? Okay, so if that's to be believed, then that's not complicated. They're just kind of using, in my opinion, screwy terminology. But I mean, I see why you would use that terminology. I would just give it a different name. Okay, so that's That's linear general. I still don't know what's up with like this bias thing. It seems like we flatten everything, and then ultimately just call the ordinary matrix multiplication. So I'm guessing that like I'm not supposed to think of like a 4x3 bias as being like a vector in some, like a vector over some matrix space. I think I'm just supposed to think of it as like a convenience way to like talk about a 7-dimensional vector in some sense. And then we have linear, which is a linear transformation applied over the last dimension of the input. This should be the more traditional thing. I don't know what this tree map thing is, but I guess it's a map from the JNP shape to the NNX state of layer. And when we do that, we get back a thing that has state on the outside. And bias is mapped to, this actually is pretty useful. So the variable state of the bias has, I guess, is like a 4-dimensional vector. The kernel is a 3x4 matrix, I believe, if I'm understanding. The type of the kernel is parameter, or param rather, and the type of the bias is param. I don't know what param is, but that seems to be what's going on. I'm a little bit confused about what this state thing is doing out here. I would have expected a map from the shape. Maybe we'll see what oops. It's going to interpret Jax tree map as a URL. So the Jax tree map is a pi tree, which I don't really think we looked at when we looked at Jax. Pi true is different from a pi tree. Okay. In Jax, we use the term pi tree to refer to a tree-like structure built out of container-like Python objects. Container-like. I'm guessing this is containers in the sense of like the Java standard library containers, the C++ standard library containers. Classes are considered container-like if they are in the pi tree registry, which by default includes lists, tuples, and dicts. So this is just a generalization of these things. I'm guessing that there's literally some piece of code somewhere that just has these hard-coded. Any object that is not in the pi tree container registry is considered a leaf pi tree. Any object whose type is in the pi tree container registry and which contains a pi tree is considered a pi tree. Okay. Let me just check one thing. All right. Okay, so this is, they have some reason for making this into a tree. I will add this to my reading list. But we don't need to look at it. Okay. Although, I was wrong. I will admit when I was wrong. I used to think, long ago, about 10 minutes ago, 15 minutes ago, I was under the impression that the Jax tree map was a map in the sense of a hash map. I now believe that they are mapping the first argument over the second argument. And that explains this output. Because this is presumably the output of the JNP shape call on the state stuff in this layer. And the tree map, I guess, is like, instead of mapping over a list, which is the traditional thing to do, this is kind of like traverse trees, which is a common functional programming thing. Maybe they had to invent or use pi trees to get that kind of behavior. Okay, and then the rest of this should just be the straightforward matrix multiplication, which they're going to call dot product. And in fact, it's going to be an affine transformation applies a linear transformation to the inputs along the last dimension. And yeah. Okay. Kernels, blah, blah, blah. Okay, cool. So that's linear. What haven't I understood about linear yet? Well, one is like nothing. I guess that's all it's doing. There's no like activation function, right? There's no this doesn't seem to be this seems to be just the affine map, perhaps, right? Or is there's no like notion of layers. There's no like fully connected layer. I think this is just a what they call an affine linear map. All right, an einsum transformation with learnable kernel and bias. I don't know what einsum is. I don't know if it's like Einstein summation. A string to denote the einsum equation. The equation must have exactly two operands, the left-hand side being passed in and the right-hand side being the learnable kernel. Okay, so here's an example of, I guess, the string you pass in NTA, HAB to NTHB. And you give it some tuple, the kernel shape, the shape of the kernel. And it's going to give you a thing back, a layer. And it has a shape, 824. Or rather, the kernel has a shape, the bias has a shape. And when you call layer on all ones, I guess maybe in this shape, then you get an output with shape 161184. I don't know what happened with the 2. I'm guessing the 84 might be from here, the bias, although I don't know. Let's find out what this is supposed to do. Einsum. Okay, yeah, this is supposed to be Einstein summation. Using the Einstein summation convention, many common multidimensional linear algebraic array operations can be represented in a simple fashion. Great job, Einstein. You know, there's a story. Who is it? Grassmann? I think the stories that what I read, I think Grassmann posted it on Instagram that Einstein had a hard time learning the algebra for that he needed for whichever version of relativity, and I think he got help from Grassmann. Don't quote me on that. Oh, I need to have double ends, but I think that's not the root of my problem. Oh, I didn't even realize they wrote a paper together. Let's read that. Where's the PDF? No. What? I don't care who cites this. Everyone cites it. I did the wrong search anyway, GitHub. All right. Well, I can't add this to Wallabag because I don't think Wallabag is going to do OCR, but I guess they did work together. So that lends credence to that story I kind of half remembered. All right. Okay, so this is just Einstein summation. That's fine. And we've got this broadcast shape stuff. Again, I'm not like a NumPy user. I'm familiar with a lot of these idioms from in programming, I guess mainly through R. But I think I have a general idea of what they do. I'm not entirely sure what broadcasting is. I think it's like similar to reshaping, right? The term broadcasting describes how NumPy treats arrays with different shapes during arithmetic operations. Subject to certain constraints, the smaller array is broadcast across the larger array so that they have compatible shapes. Okay, so it's like reusing the smaller array as much as possible. I don't know if it just does it until you run out. So if you do A times B of two three-dimensional arrays, that will give you the term by term product, as opposed to the inner product, which you, or rather the dot product, which you would get by summing this result array. The NumPy's broadcasting rule relaxes this constraint when the array shape meets certain constraints. The simplest broadcasting example occurs when an array and a scalar value are combined in operation. Okay, so they're just, if B is a scalar, we're just going to multiply by all of the indices of A. And so presumably, I don't know if I have Python here. How about regular Python? Whatever, man. All right, so that's what broadcasting is. It's just like reusing stuff. Somehow it's there. It comes up in Einstein summation. I don't know. Seems like you can get in trouble trying to Einstein some stuff that are not the same dimension or the dimensions you need them to be. But like under the hood, it seems like Python will try to like reuse values as much as it can. Okay, so that's linear, and there is like machine learning content to the linear thing. It's not just like, you don't give it the weight matrix, you initialize the weight matrix, possibly using some initialization function, possibly just random values, and then those values somehow get updated. We know how to call it. We don't, I think, know how to update it. And I'm guessing that's either that's done as part of like Optax, the optimization library, which I think is responsible for computing things like the gradient. And I think it has an update function that you have your model. And I'm guessing the Optax essentially has like peaks inside the model and iterates over all of the layers, and I guess uses the appropriate math to update. But so far, I don't think I've seen any updating logic as part of this. This stuff I think is all mutable. So where's the weights? Let's take a look at the weights variable. I don't know. We have the kernel. Is that just inside the kernel? Yeah. So when you call dot general, you pass in the kernel, and I'm guessing the kernel is the thing that has all of that contains all the weights, right? Initializer function for the weight matrix. Okay, yeah. So I'm just going to assume that's the case. Let's take a look at what is the next one? CNN? Something NN? Oh no, conv. Let's look at conv. Convolution module, wrapping lax.conv general dilated. I'm not sure that I know what dilation is. A general n-dimensional convolution operator with optional dilation. It wraps the XLA's conv operator. So strides, I think, is like skipping stuff, right? Window strides, a sequence of n integers representing the inter-window strides. Padding. Either the strings same lower, or valid is a sequence of n low high. I don't know what this means. N low comma high. Oh, I guess this is these are integer pairs, and it's like an interval notation. So the low thing is on the left, the high thing is on the right, I think is what this means. Integer pairs that give the padding to apply before and after each spatial dimension. Same and same lower. Add padding to produce the same output size as the input. The padding is split between the two sides equally, or almost equally. In case the padding is an odd number, the extra padding is added at the end for same and at the beginning for same lower. So the left-hand side dilation is if it's if there's something in there, if it's not none, then it's a sequence of n integers, giving the dilation factor to apply to each spatial dimension. So we're calling it spatial dimension. I don't think you actually need to have, as opposed to what, time dimension? I'm not sure what spatial dimension means in a general. If we're thinking of tensors as just bags of numbers, I don't know what it means to be the spatial dimension, but I think the standard use case is an image. And so I'm guessing that they mean something like an image is 2 by 2, but it has like 3 channels, maybe red, green, blue. Maybe there's an alpha channel. So I guess those would also be dimensions. So now that I'm saying this, I think this is this is a good mental model for how they're thinking of tensors. So let's just say an RGB image with no transparency information is, let's say it's a 512 by 512 image. Then 512 by 512 is a matrix. And so we can think of the image as being a 3 tuple of 512 by 512 matrices. So that's like a 3-dimensional matrix in some sense. And so I'm guessing that it means spatial dimension means that we don't dilate along the like RGB axis. LHS dilation is also known as transposed convolution. So maybe it's equivalent to transposing first and then doing convolution. Then RHS dilation is, again, spatial dimension. RHS dilation is also known as atrius convolution. Atrius? So this is conditional. It's supposed to be alphabetical, right? Conditional, where's convolution? Okay. All as conv with general padding, but the padding is specified in a shorthand way as either same or valid. Okay, so the same and valid stuff comes directly from XLA. It's exposed by the Jax layer. And then conv with general padding, maybe you tell it explicitly how to pad. Padding is what? An array slice of a pair of int64s. The spatial dims, I guess spatial dims is what? Is it an argument? For example, to indicate dimensional numbers consistent with the conv function with 2 spatial dimensions, we could use NCHW, OI, HW, NCHW. What? In the string case of dimension numbers, each character identifies by position. The batch dimensions in left hand and right hand side, and the output with the character n the feature dimensions in left-hand side with the output and the output with the character C. So C means feature dimension, N means batch dimensions, input and output feature dimensions in right-hand side with the characters I and O respectively. Okay. So they are the same character in the input, different characters in the output, I and O. And the spatial dimension correspondences between LHS and RHS and the output using any distinct characters. What? Okay, so NCHW means the first one is the batch dimension. The second one is, I guess, feature dimensions. H is maybe just used as the corresponding character for the spatial stuff. To indicate dimension numbers associated with a conv function with two spatial dimensions, I guess those dimensions are H and W. This would be, I guess, height and width. That makes sense. Then this is output, input, height, and width. And this is batch something. Input, height, and width. Maybe C is for channel. As another example, to indicate dimension numbers consistent with the TensorFlow conv2D operation, one could use batch, height, width, whatever C is. Height, width, input, output. Yeah, I mean, I don't know. I don't know what any of this is. So I'm guessing this is, you have some tuple, like 1, 2, 3, 4. I guess 1 would be like essentially no batching. We're batching one thing together. 2 would be the height. 3 would be the width. And 4 would be whatever C is. Something about spatial dimensions. Let's look at what PyTorch does. Applies a 2D convolution over an input signal composed of several input planes. In the simplest case, the output value of the layer with input size n c in h w and output n c out h out w out can be precisely described as, I don't know what it means to call the output function on ni c out or whatever is going on here, but the output, which is maybe like a function of the dimensions of ni and C out, is going to be the bias, which maybe this just means the bias depends on the C out parameter. Plus, we're going to sum from 0 to the number of C ins minus 1, the weight, which depends on C out and K. Where was K? The K is the summation index. We're going to multiply it by the input of Ni and K, where star is the valid 2D cross-correlation operator. N is a batch size. C denotes a number of channels. So C is the number of channels. I guess that correctly, I guess. So H is the height of input planes in pixels, and W is the width. So where are W? I don't know if W or H are used here. I don't see them. C is used, it's the number of channels. And maybe height and width just have to match for this to be defined. So this, let's see. Okay, this looks like it's going to be too hard to find the version that we're using. I don't think we're doing integration. Okay, so that is more or less reasonable. We have some crazy letter-based notation for specifying how things are wired up in terms of the dimensions. And it seems like really what we're doing is working around the fact that we don't have good typing information, right? So the way things are aligned, that should ideally be encoded in the types of things that they are. But what we're doing is we're like passing around like giant bags of floats, and also passing around the indices, the dimensions that you need to like reconstruct that bag into a certain shape. And maybe we would have to do that anyway, because that's that might be how you get the best speed on the GPU. But it seems like there's probably a way to do this so that the code contains the dimensions in a much clearer way, and then during compile time, this sort of dimension juggling is worked out for you by the compiler. But it seems like right now the onus is like put on the programmer to be able to do that job, if I'm understanding correctly what's going on. At any rate, I think the idea of writing an API like this is to make it slightly less horrible than if you were writing code that called XLA directly. So we have this convolution thing. So you give it the number of input features. That's a reasonable thing. The number of output features, that's a reasonable thing. You give it the kernel size, which is some tuple. This, I guess, is a 3 vector, probably. You tell it what padding you want, and you give it the RNGs. And then you get a layer, and the layer has a kernel. And the kernel has shape 3, 3, 4. 3 for the input features. 3 maybe for the kernel size, and 4 for the output features. And then the bias is the same size as the output, which you would expect if they're also doing so I'm guessing bias is just again a thing that we add at the end. And here's circular padding with stride 2, etc. Okay, so that's some convolution. And when you call applies a potentially unshared convolution to the inputs. I don't know what unshared means. I guess we're not sharing it with something. And the arguments are input data with dimensions batch dims, spatial dims ... features. This is the channel's last convention. So your batch dimensions are first, spatial dimensions are second, and then features are last. That is NHWC for a 2D convolution. So the channels are last, and NDHWC for a 3D convolution. I don't know what D is here. Note this is different from the input convention used by Lax general dilated. Rather, Lax conv general dilated. And I still don't know what dilation is. Maybe we can look that up quickly. Nope, not medium. I don't want medium. These are all like explainer sites. I'll figure it out later. Something about skipping stuff, probably. What's dilated convolution? Explain it like you're totally wasted. Instead of hitting every spot, you skip a few, leaving gaps. Okay. So you're like skipping pixels or something so that it, I guess for the same number of values of the convolution, if you're skipping every other pixel, you can cover more of the image with a smaller convolution-y thing. So what is stride? I thought that was something we do. So stride length is the distance covered when you take 2 steps. No, that's foot stuff. I don't care about foot stuffs. When performing convolution operation, the stride determines how many units the filter shifts at each step. Okay, so that's all right. So I think what dilation is like the filter is skipping stuff, and then stride is like you might skip some stuff as you're like stepping along. At least that's how I'll think about it. Okay, so this is linear conv transpose. I'm going to guess some transposed version of the convolution. Convolution module wrapping Lax conv transpose. Cool. Okay. And then we have embed, which is an embedding module. And we're, let's see. Embed has some number of embeddings, some number of features, which here is 3. And we can ask for its state. And we get an array. The state is some array of numbers. And I guess the idea is that this array is going to consume some vector of inputs and map it into what we think of as the embedding space. So the num embedding is the number of embeddings slash vocab size. I don't know if this is divided by vocab size. Let's see. A parameterized function from integers, 0 embeddings, to features, dimensional variables. This module will create an embedding matrix with shape, number of embeddings, features. When calling this layer, the input values will be used to 0 index into the embedding matrix. The input values. Indexing on a value greater than or equal to the number of embeddings will result in an NaN value. So not a number. So call embeds the inputs along the last dimensions. Embeds the inputs along the last dimensions. The inputs are input data. All dimensions are considered batch dimensions. Values in the input array must be integers. It returns output, which is embedded input data. The output shape follows the input with an additional features dimension appended. Okay, so when it says along the last dimension, I was interpreting that to mean that we're going to overwrite the last dimension as kind of an out parameter. But it seems like what they're really doing is just appending another column. What I don't understand is if this is like an embedding in the sense of like a textual embedding, how do we get from the world of text to the world of numbers in the first place in order to apply this matrix? Attend is attend over the embedding using a query array. This is something attention related. Args is a query, an array with last dimension equal to the last dimension. I'm guessing this means like, well, I don't know. If it's a NumPy thing with some shape, then maybe the last tuple of the shape, that the last dimension, equal to the feature depth features of the embedding. And it returns an array with final dim num embeddings corresponding to the batched inner product of the array of query vectors against each embedding. Commonly used for weight sharing between embeddings and logic transform in NLP models. So we're going to promote the D types and just call the dot, JMP dot of the query with embedding.t. Query is the array passed in. What is .t? Wait. Yeah, what is .t? Oh, it's the thing that we get from here. And the thing that gets sent to embedding is whatever promote D type does, the embedding value, which I think is essentially the kernel. Is that right? Maybe NNX param is the thing that has is like some pointer to the kernel essentially. Let's find param. Let's find the param in the documentation. Yeah, okay. So dynamic state is usually stored in nnx.params, and static state, all types not handled by Flax, such as integers and strings, are stored directly. So params is a wrapper around, I guess, what I'll think about as mutable state. It calls it dynamic state. So these are the things that I guess I see what's going on here. So params is essentially a wrapping type that prevents you from monkeying around with the internal state that's relevant to the machine learning. And the way it prevents you from monkeying around is it's so complicated that people are not going to want to assign to it directly, I think is really what's going on. And among other things, this probably contains the kernels, right? So let's see if we can find class param. I'm not signed in. What happened to my login, GitHub? I meant to capitalize param. Okay, so it's in variables. The canonical learnable parameter. All learnable parameters in NNX layer modules will have the param class variable type. And so it just says pass. Pass. Why should you do that to me? Okay, so this is a different part of NNX. I think that's, I would have to look at that differently. Okay, so that's linear. I did not get even close to what I was I was hoping to do. So let's take a look at attention and see what that looks like. So we have we've got this dot product attention weights, which I'm going to guess is kind of just like a convenience function. Computes dot product attention weights given query and key. So you give it a query, you give it a key, and attention is like conceptually they want you to think of it as a kind of key value store, right? I forget exactly how it works. You have presumably you're learning some matrix, let's say, and maybe you want an output, which are the values, and you have two actions, I guess, one on the left and one on the right. So maybe you act on the maybe you simultaneously act on the left with the query and on the right with the key. And so you would need the dimensions to all line up for that to be the case, but we'll see if that's what's actually going on. So used by func.product attention, which is what you'll most likely use. But if you want access to the attention weights for introspection, then you can directly call this function and call einsum yourself. So queries are queries for calculating attention with shape of batch, queue length, num heads, QK depth per head. I don't know what depth is. I really still don't feel like I understand what's going on with batch. Although, now that I say that out loud, I think there's really only one thing batch can logically be, which is that we want to call this operation on a bunch of different kind of like independent vectors, but we don't want to keep paying the overhead of handing off to the GPU. So we just bundle our vectors together. So I think batching is like a I will conceptually ignore the batch dimension. I'll set batch conceptually to one batch dimension, and then just assume that you have like one of each thing that you're trying to do. The key are keys for calculating attention with shape of batch, KV length, num heads, QK depth per head. Bias is bias for the attention weights. Mask is mask for the attention weights. And we have some broadcast dropout, which is bool. some Boolean about whether to use a broadcasted dropout along batch dimensions. Okay. And then a random number generator to use dropout. I'm guessing what's the alternative to broadcasting dropout? Using the same dropout for each, or having a different dropout for each, or something like that. And then we have some dropout rate, and then whether dropout is deterministic or not. I'm guessing randomness is really nice to have, but if you're passing in the random number state, I don't know why you wouldn't be deterministic. Deterministic has the nice factor that for testing it's easier to test or debug if something goes wrong. And then d-type imprecisions in module. And the output has shape, batch, num heads, q length, kv length. So keys has kv length, which is also the part of the, no. These are both part of the shape of the output. So both q length and kv length. So we calculate the attention matrix. We take query, call shape -1. Okay, so shape is just a vector, and -1 is what the last element, I think. And then that gives us the depth. And the query is we're going to take the query vector thing, which I am going to believe is a vector. It's not really. It's got this batch stuff and other attention stuff. We're going to divide it by the square root of depth. To, I guess, normalize it. And then we have this attention weight shape is this thing. And then the attention weights we're going to get by Einstein summing. I don't know what the ... convention is with this Einstein sum stuff. But I guess these are like indices. So QHD, KHD, and somehow we're going to return HQK. I don't know how this string... I'm not familiar with this Einsum convention with these text strings. I'm not sure like what kind of like sigma notation these correspond to, but it seems like this is a common convention in this space. This is not something that Jax or Flax is inventing. So somehow we're going to sum stuff up as indicated by this string, and then we'll apply bias. It's just we're going to add it if bias is not none. And if mask is not none, we've got this like f info, which I originally read as first in, first out, but this is just f in, whatever info is, I guess, of d-type min. That's the big neg, I guess, big negative number. And then we're going to look at the mask where the attention weights are big neg, and those are the attention, and those will, I guess, be everything that's not masked. No, what? I guess everything that's in mask, maybe we're going to replace with big neg here or something along those lines. And then we're going to call softmax on the attention weights. What are... I think attention weights are conceptually at least a matrix. I guess I didn't realize you could call it softmax on a matrix, but why not? I guess it would just call term by term. X-axis computes the function which rescales elements. Okay. So X is supposed to be array-like. So maybe the weights are, maybe this weight thing is supposed to be a vector. Okay. And if module, whatever that means. So if module is non-null, Then we're going to call so, whatever this is, intermediate attention weights, et cetera, et cetera. Okay, and if we are not deterministic and dropout rate is bigger than 0, then the keep probability is 1 minus the dropout rate. Yeah. And if we're supposed to be broadcasting dropout, then the dropout shape is going to be a tuple of, we're going to get a bunch of ones in the key.ndim minus 2. So two fewer dimensions than the key ndim. I guess key is probably the random number key, right? We're getting a bunch of ones, and we're adding the shape from the attention weights, the -2 of it. Or I guess getting everything after the second. I'm not sure what we're keeping in the 0, 1, 2 indices. I think that's what that notation means. It's been a while since I've done a lot of Python. Okay, and then the stuff we're keeping is we're going to do, I guess, some random Bernoulli trials, passing in the RNG with the probability of keeping in the dropout shape. Just the shape, which is this thing. And then the multiplier is we're going to take keep, turn it into the D-type thing. I think D-type is something we can pass in to kind of control the type. And we're going to divide keep by the keep probability as an array. And this is presumably this should result in some ones and zeros, because ultimately we're just going to multiply it by the attention weights. I'm not entirely convinced that this is ones and zeros, but Bernoulli should return what? Ones and zeros. That's keep. And then why are we dividing it by keep prob? And where did keep prob come from? Yeah, now this is mysterious to me. So I misspelled random, but that's okay. Let's look up the Jax. So it does return a random array with Boolean D type. Okay. So does that mean they're? I guess that means they're maybe that means that they're literally Booleans. So they're trues and falses. And we're going to divide by the keep prob for some reason that I don't know. And maybe that converts them to ones and zeros. I'm going to ask ChatGPT about it. So in this code, when we set the multiplier variable, why are we dividing? Oh, I should tell it the code. ChatGPT can't read my mind yet. When applying dropout, the non-dropped weights are scaled. Oh, okay. Oh, okay. So they are supposed to be scaled. Fine. All right. I didn't realize they were, but that's reasonable. Okay. So then that's this. Yeah. So I also wanted to know. So let's figure out what the key and value thing is again. So here it is in summation notation. I don't know if this is some sort of bracket. The key aspect of the attention mechanism can be written schematically as we're going to sum over the index I, and I assume this is the inner product of the query with this key and whatever this means of value. I don't know if the okay, so the angles denote the dot product. This shows that it involves a multiplicative operation. But what does it mean to call it on value? Let's try an image search. Maybe we can find the what is attention? So an attention function can be described as mapping a query and a set of key value pairs. So we have a single query and a set of key value pairs to an output, where the query, keys, values, and outputs are all vectors. The output is computed as a weighted sum of the values, where the weight assigned to each value is computed by a compatibility function of the query with the corresponding key. So there's a compatibility function of the query with the key. The key and the query are both passed in, and it's a weighted sum of the values, where the weight assigned to each value is computed. So the weight assigned to each value, this I think is just describing a dot product of the values with this thing, with the result of the compatibility function. Scaled dot product attention. We call our particular attention scaled dot product attention. The input consists of queries and keys of dimension d sub k. So the queries and keys have the same dimension and values of dimension d sub v. We compute the dot products of the what? Of the figure 2? No, of the query with all keys. Yeah, we compute the dot products of the query with all the keys. So maybe the keys are the matrix. Divide by square root of d sub k and apply a softmax function. In practice, blah, 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 blah. I would like to see it in notation. Is that possible? So, okay, this is, I guess, good enough. So, Q and K must both be matrices. We're going to matrix multiply them. We're going to scale the result. Optional masking, we'll assume that we're not doing it, and just take the result. And then we're going to matrix multiply the product of Q and K with V, which must also be a matrix. That's scale dot product attention. And then multi-head attention is VK and Q are linear boxes. I don't know if linear means the same thing that linear means in the code, essentially like a learned affine transformation. But let's assume that that's essentially what it is. So we have three linear maps, three matrices. I'll assume bias is 0. And they all get fed into the scaled dot product attention, which is here. So that we just do this. We just, wait, why is Q over here now? I don't know. And what does it mean for K and Q to have multiple things? I guess that what it's showing here is that now V, K, and Q, I guess, correspond to multiple linear maps or affine maps that are maybe trained somewhat separately, possibly via dropout is what's going on there. And then they all get this treatment. We multiply K, Q, and K. Definitely do some scaling. Definitely do soft max, maybe mask in the middle, and then we multiply by V. And this is it in notation. It's just matrix multiplication with some scaling and softmax. Okay. I was imagining this kind of like left-right action where we had some learned matrix in K and Q are vectors, but they're matrices, and that's all straightforward. Okay. So that's attention. And then let's figure out how we get multiple matrices. Multi-head attention. Instead of performing a single attention function with D-model dimensional keys, values, and queries, we found it beneficial to linearly project the queries, keys, and values H times with different learned linear projections to the appropriate dimensions, respectively. On each of these projected versions of queries, keys, and values, we then perform the attention function in parallel. I'm not sure yet how we get these projections. I assume that these are learned. And it's possibly learned through dropout, although I'm not seeing that obviously mentioned anywhere. Okay. So that seems a little bit like, I always call it bagging, but there's a standard operation where in machine learning, in life in general, there's a kind of like redundancy of to avoid something like overfitting a single model. You kind of, instead of like super training one large model, you kind of train some smaller models, or not necessarily smaller in dimension, but they each get less love because you have the same amount of data, but you train smaller models and then you somehow use their diversity as a strength. Just like in human organizations, diversity is often a strength. In the biological world, diversity is a strength. So it's kind of using the randomness and the diversity that comes from the randomness as a source of strength. And that has, I'm sure, lots of different names, but that's conceptually, I think, what's going on. Okay, so this is that function that does dot product attention weights. And then at least let's see, so here's dot product attention. This should, I'm not sure really how it's different from weights, but I guess weights is just the one computation that is doing. So we do have dropout here, but we're not applying it to get, I guess the multiple, the different maps. This is like a single thing. So I guess there's dropout in each key. So we're giving it a single query, I think, and a single key, aside from batching, which we'll ignore for now, as opposed to the having all of the multiple things at this level of the code. And then dot product attention is going to compute the dot product attention given query key and value. This is the core function. Based on that paper, it calculates the attention, assuming this is the right paper, same paper, and not like some follow-up. Yep. Okay. So it calculates the attention weights given query key and key and combines the values using the attention weights. So we've got this promote D type. We're doing some assertions about the shapes. And then after the assertions, we just call dot product attention weights, which was the function we already saw. And then we return the weighted sum over the values for each query position. I had thought that this was going to be just a dot product, but I guess it's the Einstein summation thing. And then multi-head attention is we have some number of heads, input features, QKV features, which is dimension of the key query and value. Okay, so there's a single dimension, I guess, output features, etc. And we have some init function, and then I kind of want to just see if they have like, well, let's see. So they have the number of heads, in features, etc. Just setting up, and if the QKV features isn't divisible by the number of heads, then we have some error. Memory dimension of QKV features must be divisible by the number of heads. Yeah. And then the head dimension, we're going to get by, I think this is integer division, dividing the QKV features by the number of heads. So why does it have to be divisible? I guess we're, each head is some bucket of QKV features. Is that right? So they're not like overlapping in a sense. And I guess that's mainly for parallelization then, rather than redundancy, like I was thinking. No? Well, I don't know. I'm not sure. Maybe you know, and you can tell me. Okay, and then we get this linear general thing. We are using functools partial, which I think is just like currying. And we've got linear general, we pass in the number of features, et cetera, et cetera. And then we project inputs Q into multi-headed QKV. Dimensions are then batch, length, and heads, and features per head. So linear underscore general is this curried linear general thing. And I guess we've curried it just so we can do that. Just so we can pass in the RNGs, perhaps. And these are now separate, like linear layers. But in features, out features, and then where's head dim? Are we using head dim anywhere? Here. Okay, output features is now, instead of being a single instead of being a single number, which would give us a vector output, we now have a tuple, which is the number of heads, comma, the head dimension. And this is, I think, now showing us that we're supposed to think of the linear general really as just kind of like giving us parallel operation over the output thing, the output features, I think, as opposed to being some kind of like fancy generalized multilinear map. Okay, so in other words, this tuple here, I think is just, did I just close the PDF? If we had the PDF open, it corresponds to the kind of like the card notation showing that there are multiple maps. And so in that picture, there are multiple linear maps, but I think that linear general is just considering them as one single class that holds the multiple maps internally. And then if I was understanding correctly what was going on with the kernel, really those kind of get turned into one larger map, and it's just that the different parts of the map don't interact with each other. So it's kind of like maybe like a direct sum of maps and vector spaces. Okay. And so these are the query key and value thingies. And then query ln, I guess this is layer norm. I guess we have a single norm layer and a single key layer norm, and maybe we just use it on each of them. If self normalize QK, then the query layer norm is going to be defined as opposed to being none. Similarly for the key layer norm. And the output is a layer general. The input is going to be the number of heads and head dimension. So we're getting the input from the output of these things that had the multiple linear card thingies, linear thingamajigs. I don't know what the right term for. I don't think it's a layer, but doodads. So this stuff is plugged. The output of that is plugged into the input of this. Is what's going on, I think. And then the out features, the output dimension is now, I think, just a proper vector, because is out features an int? Yeah, it's either an int or nothing. So now we have a proper vector as output. The tuple output features was really just used, it looks like, in service of wiring up this stuff internally. And we have precision and dot general and stuff. And we have some possible cache. And then when we call it, applies multi-head dot product attention in the input state. It projects the inputs into multi-headed query, key, and value vectors. Heads. I could have called them heads. I guess that's what they're called. They're not called doodads. They're called heads. So and it applies dot product attention to and project the results to an output vector. If both inputs k and inputs v are none, they will both copy the value of inputs q self-attention. Okay. And so this should look pretty straightforward now that we've done all of that work. So query is self.query of inputs q. So query is the linear map. So this is taking the input, I guess applying the linear map stuff, and similar for key and for value. So these are now, the query key and value, I think, are now multi-headed. And if we are normalizing, then I guess we are normalizing all at once. So we are normalizing the multi-headed stuff, normalizing query and key projected value, stabilize it. So I guess if I'm understanding this correctly, we're not necessarily, it seems like we're normalizing using all of the data across the heads at the same time, as opposed to normalizing each head independently. Although I'm not sure that that's the case, because I don't know how to think about most of these NumPy style operations. And then we have this thing during fast auto-regressive decoding. We feed one position at a time and cache the keys and values step by step. So decode is set to first from decode self.decode. I'm not sure I saw where decode was. And with some error message. And if we get a decode, this is some caching stuff, which I'm going to ignore. And then we see some dropout stuff here. And then we call self.attention function, giving it the query key value, etc. And self.attention function is presumably going to ultimately call the attention weight stuff. There's some stuff about masking, combining masks. Oh, attention FN. Okay, so you can pass it in as a callable. Huh. And I guess the default is it's just set to dot product attention. All right, so how long have we been here? About 2 hours. I'm going to call it a day there. I think I've seen enough of NNX now to have a feel for like how information is threaded through. I've learned a lot about what things are called in the machine learning world. Also, like what people care about in the machine learning world. I've seen a lot of the NNX comes from a history of things like TensorFlow, PyTorch, and a lot of the conventions that we saw in those kind of earlier attempts to figure out how to make machine learning fast are showing up here. And I think that's really about continuity for the data scientists and other folks, so that the knowledge that they learned with those older systems is still relevant to this newer system. And I'm getting a better feel for also for the math, kind of like none of the math seems really complicated at this point. It's more like which bits are they using, what conventions are they using, and is that making sure I can translate the way that I usually think about